Okay, welcome to this second lecture of MCS 471. So MCS 471 is an introductory course in numerical analysis. And this is our second lecture. In a way, it is the first lecture on the subject. So lecture one was on the course, a bit about Julia, and then also about the fundamentals. What we will do today, and you can see the outline here, is we will define what is numerical analysis, what is floating point arithmetic, and in general, what is it actually that we have to be concerned about if we want to compute accurately. So we have a full agenda, so let's plunge in immediately with the definition or a definition of numerical analysis. So here is a short definition. So numerical analysis is the study of algorithms for problems of continuous mathematics. So I got this from SIAM News. SIAM is the Society for Industrial and Applied Mathematics. So it is a good definition. It's not the definition, but it captures very much the essence of the subject. We care foremost about accuracy, but equally we care for efficiency. So these are the two guiding principles in numerical analysis. So we have to work with an imperfect world. You could see where the word approximate comes from, but also in continuous mathematics, everything is continuously evolving and changing. So we have approximate input and we also obtain approximate output. So numerical analysis is the focal point of the course. There are two related disciplines, a little bit related to the precursor course, MCS 320, which was on symbolic computation. Here it's stated as computer algebra. Computer algebra is very useful to formulate and also reformulate our problem. So we will see in this lecture an example of a reformulated calculation. The other discipline is related to applications. So scientific computing is the discipline that applies mathematics to solve scientific problems. Also, if you like, industrial problems. So this is again pointing at the sequel course, Industrial Mathematics. All right, we make errors. So our mathematical models are what they are. They are a model, a simplification. If you like, sometimes a cartoon. So we will be using Taylor series throughout this course. Calculus is one of the fundamentals. So truncation errors are the first source of errors. We often, and most likely, numerical analysis is motivated to solve scientific problems. The data is obtained by observations. So we can compute extremely accurately, but sometimes the input data is is known to very limited precision. All right, then we actually touched on the fundamentals of binary numbers and arithmetic. So 1 over 10 is 0.1 because we have 10 fingers. It's not exactly representable in binary. And that leads to another source of error, representation errors. So even a nice number as 1 over 10, a nice rational number, already leads to a representation error. And then the last source of errors are round-off errors. We will see in this lecture how round-off errors occur. So regarding accuracy, we ask actually two important questions. If we change the output a little bit, if we change the input, then how does the output change? And actually, I started wrong this sentence. We can also think backwards. So if we have the output, and if we change that, what will the input change? If we have a nice problem, the size of the changes in the input will be related to sizes of the output. Okay. The other question is what happens with the round-off errors? We will have good problems and bad problems, so that's the first question. We also have good algorithms and bad algorithms. So the second question relates to numerical stability. So we will be saying that a calculation is numerically stable when the round-off errors remain of the related relative to the working precision. For problems, we have numerically well-conditioned problems, and these are the problems which are not too sensitive to changes in the input. We can do something about numerical stability, namely think about better algorithms. Numerically badly conditioned problems, the only thing we can do them is reformulate them. Actually not solve the original problem, but solve a problem that is better, a better problem, solve a different problem. How do we measure errors? Most likely, well, here is the obvious definition. So we compare the number that is exact with the approximate error, so the computed error. So that gives the absolute error. And then we have the relative error. So the absolute error is the obvious one, but actually we care mostly about the relative error, which takes into account the magnitude. These are formal definitions, but more common sense. If you lose $1, but you have $3 million in the bank, it's not that much of a problem. If you have only $10 and even you don't have them in the bank, and then you lose $1, that's a much greater loss. So be careful about definitions. And of course, relative error only makes sense if you can divide by the magnitude. If you don't have any money, a loss can't occur. So the relative error is not defined when the number is 0. Speaking of 0, let's take a look at these three numbers now. They all look very different. So if you look at these numbers, they couldn't be more apart from each other. But they have something very important in common. They are written in scientific notation. And if you look at them a little bit more carefully, what they actually mean, then actually you see that they're all actually very, very tiny. So in numerical analysis in this course, every real number is represented in scientific notation. So we read the numbers from right to left. The other issue is that here the we're giving in their full glory, in their full precision. These numbers typically, these three types of numbers show up as errors, and then actually we limit what is before the exponent. So you can see that what these numbers actually more accurately represent is actually numbers that are very close to 0. So this is a calculation that happens a lot in practice. You have to decide whether something is 0 or not. So that's one of the problems that numerical analysis have to focus. When is something 0? All right, so now the lecture gets more technical. How do computers represent real numbers. Well, we don't have real numbers in a computer. We have only bits, but do have floating point numbers. And floating point numbers, if you like, are very similar to the way we see numbers. We see real numbers in scientific notation. We see a sign, we see a fraction, and then we see an exponent. And these are the three ingredients for what constitutes a floating point representation of a real number. And with that, we can also make more formal what we mean by the representation error. So in scientific notation, we actually see the E, and now let's not confuse the E with the transcendental constant E. So E is saying that there is an exponent following. Here in the compact representation, the E is actually more important than the fraction. So the E is actually stored first, because you can compare numbers very quickly if their exponent differs. So internally, the exponent will start at the second bit. And then the end of the representation will be the fraction. So one word that is not explained here, that is the normalization. So that will become clearer. What is actually important also here is that we only have a finite number of bits that are used to represent a floating point number. All right, here is the floating point format. We distinguish essentially between three different levels of machine precision. So machine, I should say hardware. So the hardware typically supports three different precisions, 32-bit, 64-bit, and 80-bit. Our default will actually be the float 64, the 64-bit float representation. So there are 64 bits. The first bit is the sign. The next 11 bits are the exponent, and then we have the bits in the fraction. So the compact representation is in a sequence of 64 bits. And here you see the convention. The sign bits is 1 if you have a negative number. We then have the bits in the exponents, and then the bits in the fraction. I mentioned the normalization. So what does the normalization exactly mean? The normalization means that the leading bit is actually different from 0. All right, so let's time for an example. So we are 10 slides in. Let's look at a very simple, but yet not a non-trivial number system. So it's a binary number system, basis 2, and it is a hypothetical number system. So we have a very specific hardware where we have only 3 different exponents and only 2 bits in the fraction. And in that number system, we can only make 8 possible floating point numbers, and we can enumerate them here. Why only 8? Well, the leading bit has to be different from 0. So actually, the leading bit after the dot is always a 1. So in some sense, why is there actually a position there? Well, there is a position, because we can also do something with a not normalized number. So that's why there is also where we write the 1. So here you see a dictionary, if you like. At the left of every equation is the full expansion of the number. And at the right is then the decimal notation. So in here you see the number line, where it is a very toy example, but it represents a truth also for any number system. That is that between the interval 0, 1, the repetition errors are a lot smaller than when you get farther away. So one way to reformulate a problem is to make sure that your numbers are not too large when you manipulate one. So we actually, what the number line also shows is that we can't really present real numbers, but also the rational numbers are not represented exactly. So we have a huge gap here when the numbers start to get larger. The gaps are more acceptable when they get smaller. So the errors in the representation here assume rounding. All right, so now we have another important definition, and perhaps it's even the most important definition of this lecture. What is now machine precision? So machine precision is actually the smallest number that you can add to 1 and still make a difference. So I'm saying this here in another way than it is written, because what I say is the practical implication of machine precision. If you make sums of very large numbers and you don't sort them in the correct manner, then actually at some point you can keep adding and adding, but you don't make a difference anymore, which is kind of frustrating. So here the definition is also a formula. If you know the basis in your number system, for us with our 10 fingers, the capital B is 10, but in a computer it's 2. And if you know how long the fraction is, then actually you can compute that number that is the machine precision. So floating point arithmetic is rather very strange. You can start adding numbers and you don't see a difference. Things don't add up anymore. But also the order in which, and that's actually because the order in which you make the calculations is different. So here is a very simple example. Perhaps I will actually highlight it. So what this actually means that epsilon is the smallest number you can still make a difference. So at the left you won't have that epsilon, but at the right actually you do have that epsilon. All right. What does this mean? Here's some examples. So we have the fraction. So if you evaluate the formula, then you can see what the precisions are. So you can see what it is in bind, and then you see also the approximations in the scientific notation, so the translation in our decimal number system. So we have approximately 16 decimal places correct when we work with 64 bits. That's the bottom line here of this slide. All right, so we have an approximation for real numbers. What is the smallest and what is the largest number that you can make? Well, what is the smallest and the largest exponent? So for the different number systems, you can see the exponent ranges. And we see the values for the exponent that you can make. So there are special numbers. So sometimes if a calculation goes bad, you see the NaN. That's often typically if you do something that is out of range. The not a number. So there is a specific way to encoding this. There's also a way to work with infinity. And for numbers that are not normalized. So the exponent is then entirely 0. Okay, time for another example. Let's go back to Julia. Exercise 0 of lecture 1 was to install Julia on your own computer. If that didn't work out, or we are living now in the time of cloud computing, don't worry. Here is a co-calc session where after the welcoming stream, so I'm actually not really using co-calc in the proper manner. See the green letters, sign up. I did not sign up here. So I will just, today we are running Julia as a calculator. We're using it as a calculator. So the Jupyter notebook, the first two letters stand for Julia. So we have the first kernel where we click on the Julia programming language. So that brings us to our second screen. And here you see the red letter already. Sign up or you will lose your work. This work is not saved. So Julia and Jupyter are both critical ingredients in this course. We will use Jupyter to document our calculations. So the other important point I want to point at is that this is a computational class. The code that we are executing is assumed to be logically correct. What is important is actually that we can also document and justify and explain our calculations. So a Jupyter notebook has cells that contain instructions. So here we use it as a calculator, but we can also use it as a programming environment. So there is the code, but what I highlighted, what I circled, is that any cell can also contain text. So we have the two text cells here that explain and kind of document our computations. Julia, for every so it is an interpreted language as well. So be mindful here of the dot O. So if I do simply 2, then it will be assumed to be an integer. So here I'm forcing to go to the floating point. And here you could see how I computed the value of the smallest exponent. A nice feature is also that for every 64-bit type, I can ask for the internal representation. And here you see indeed the smallest exponent that I can represent. That's the smallest exponent. And then let's try this too for the largest exponent. And here you actually see that what this is indeed. So we do have the largest exponent that we can represent. So we have 11 bits, but one of those bits is actually reserved for the sign. All right, I'm using Julia here in a terminal to do exactly the same computations as in the Jupyter notebook. Okay, we can ask for, now we had the smallest exponent and the largest exponent. We can also actually ask for the smallest number that we can represent, and that is not the smallest number, smallest positive number, different from 0, and that is not a machine precision. So on a computer, everything is discrete. So the floating means that the normalization of we try to be as accurate as possible. So the most accurate representation of a number is actually working the normalization. So what is now the smallest number that you can represent? Well, think about the example of the number line. We can ask for the next float after the number 0. And with the bit string, we actually see that that smallest number is actually a number that is not normalized. We can also ask what is the largest number. So there is the next float and the previous float. And infinity, even though there's no computer, and there's never going to be ever a computer large enough to represent infinity. But here you can see that we humans, we can invent, and we mathematicians, we can invent symbols. So symbolically, we have this predefined inf, and we can ask what is the previous float before inf. So just before you hit infinity, well, we have the largest exponent that we encountered earlier, and then we have everything is a 1 in the fraction. And you can kind of see what happens then, this number, how you can actually make it, how you can start multiplying the largest exponent with actually the relationship here between the largest number and actually the machine precision is exemplified here in this relation. Now I realize that this lecture goes fast, so we have seen the most important definition, the machine precision, and here I'm already using it in one of the important relationships between what is the largest number, the largest exponent, and the machine precision. So this equation here, which is exemplified with the bit string, is explained here. So we are doing calculations as with a calculator, but our computations are not far from being trivial. So if this takes some time to digest, and if this is very technical, you're not alone in this. All right, I will move on. Arithmetic. So here we use, in this lecture, we do some very important calculations, and we see how they can be done in Julia as well. But the purpose of this lecture is actually that we can kind of understand, by simulating the floating point arithmetic, now going extremely slowly, the cause of the representation errors and the rounding errors. So the purpose of the section now is to indicate where the rounding errors come from. And in particular, what are all the operations that are happening inside the computer when you add two floating point numbers. So it's very quite possible, if you took a good course in computing literacy, an introductory programming course, that you might have covered this. But so in that sense, this slide here is a little bit what everybody needs to know about the floating point arithmetic, but it's too critical to be left to the fundamentals. So let's look at two numbers in an imaginary but still realistic number system. So it's imagined because we have only 4 bits in our fraction. So that is for the sake of representation, but also for us to verify all the computations. So there are many steps to adding two floating point numbers. They are summarized here in 4 steps. So actually, pipelining inside the CPU arithmetic has more stages, but let's focus on these 4 stages here. The first thing that happens is that we do the denormalization of potentially one of the numbers. If both numbers have the same exponent, then denormalization doesn't need to happen. But here we actually are adding a number that is much smaller. So the second number is here normalized but we need to denormalize it. So to bring it under the same exponent, a bit similar when you add two rational numbers, you bring under the same common denominator. Here we must have that both numbers have the same exponent. So we look, scientific notation is important. So we first look at the exponents. If they are the same, we can skip step one. But here they are different, so we need to denormalize. After the denormalization, so everything is here the same exponent. So the exponent is here just added, but it doesn't matter in this stage. At this stage, we actually work with a longer fraction, and we do the binary addition. So the binary addition, I will not go through this in great detail. So the carryover is the same, follows the same rule as the decimal. It's quite easy to get tripped up by this. So here you see the result, how the ones that are least significant in the second operand are actually propagating through. So this addition, for the sake of our calculations, is performed exact. So no errors have happened so far. But here you see where the round off actually does happen. And the round off here is also with chopping off. And here you can see that the result of the round off is not normalized. So we are going to round, but we are with 4 decimal places. We're going to add this 1, and the 1 actually flips all the ones to 0, and then pops before the dot. And this is still an exact result that then gets normalized. So the normalization means that the exponent is raised. So this is a critical slide. What I actually want you to do in the first exercise is that you translate all the operations into our familiar decimal notation. What is the number x in decimal? What is the number y in decimal? And you can see that I can actually say as part of the answer already, we get the number 8 out of it. And how does the number 8 come from adding these two numbers, x and y? So the exercise is actually redoing the calculations, but now verifying why 8 comes up. So understanding that the 8 is there. And that is a paper and pencil exercise. But later in this lecture, I will indicate how you could actually also verify this with a computer. All right, we have an error. Some errors are benign, some errors are not. Okay, I said that you could skip the first step when the numbers are aligned. Here we have a case like that. So two numbers have the same exponent, and instead of adding, we are subtracting this time. The subtraction in binary may be again a little bit awkward for us with our 10 fingers, but trust me on this. So we are doing the subtraction, and we get to a number that after normalization is a rather small number, but what is actually most important is that to normalize, we have to insert 3 zeros. So what's the point? The 3 zeros are harmless, of course they are. Zeros are very nice numbers, actually perfect numbers if you like, to mathematicians. But to numerical analysis, we have to be a bit wary about 0. I tried to indicate this already in the slide with the scientific notation of the numbers. So here is the problem. We started out with 4 bits of significance. All bits were actually important, and we have inserted 3 zeros to normalize the number. So in some sense, with that number, we have only 1 significant bit anymore. This appears to be completely harmless. And at this point in time, it's not. So this is a difficult technical lecture, I understand. So at this point in time, we cannot really understand why this is actually a problem. But let me give an example. So this is an example where often one must reformulate a computation, and here it's called restructuring a computation, because if you do it in the correct, in the way as the formula is written, you will get exactly 0. So we are again in a very hypothetical number system. So here there are 2 things that are special about this. The basis is 10. So in our paper and pencil arithmetic, we will often assume that we are working with our 10 fingers. So on the previous slide, we had something that was not 0. Here we have something that equals 0. And actually, 3 is not equal to the square root of 9.01. So we can actually get a more accurate result. 0 is actually completely wrong, if you like. We can get a more accurate result if we avoid that subtraction. And here we can avoid the subtraction by actually squaring. And then instead of subtracting, so the rule of thumb is often that be careful when you subtract numbers of the same magnitude. So here we still do a subtraction, but numbers are actually better. So 9 and 9.01. So actually here we don't get 0 when we do the difference in the numerator. And then we actually get something that is very close to the accurate result. So here we get a result that is actually fairly accurate by restructuring the calculations. So we also do more work. So in a way, we do more computations than the original formulation. So we are caring about efficiency, but sometimes efficiency, we have to do more work to get more accurate results. Okay, last section. So for once, I'm actually not going over time. Very good. So Julia has actually the type big float, which uses arbitrary precision floating point arithmetic. So we have the hardware supported arithmetic, and one can say that numerical analysis is confined to the hardware arithmetic. This is a very strong point of view. One can often extend the precision, extend in both ways. So you can restrict your precision to 4 bits. And the first exercise you could essentially also verify with big floats, which actually are now small floats if you use only 4 bits. Now the arbitrary is also still an illusion. Our computers are still finite in power, so one has to be careful by not pushing it too hard. But that's one way to extend floating point precision. The other way is to use the hardware arithmetic but work with intervals. So we will not explore this here further, but often these are additional tools that the numerical analysis can use. Computing results in a higher precision or with intervals can actually be very beneficial. All right, so now we get towards the end of the lecture, and I should actually say what you should actually really know about it. So these are two additional exercises. So in a way, they are kind of very diminutive, so they are at the end. But if I can motivate you, so these are two formal final exam questions. And they are very much similar and alike. So what is important about the exercises is that you try them yourself. So looking at solutions of formal exams, former midterms will help you solving this. But if you go immediately copy and pasting, you may lose the benefit that you have thought through. So I can actually almost tell you the answers. So what is the machine precision? Evaluate the formulas. The base of your system raised to the power the size of the fraction. And in evaluating the formula, there are things that can go wrong here. So note that the exponent always in machine precision is negative. So if you know what is machine precision, then that's obvious. But if you're evaluating a formula, that is not. Similar with the first part of exercise 3, which is an alternative phrasing. What is the smallest positive floating point number? Again, we have seen a formula for that, but that's the basis for raised to. So now actually you take into account the size of your exponents. So what is the smallest exponent that you can represent? So again, that smallest positive number needs to have a negative exponent. Obvious, but can go wrong if you just evaluate the formula, as you will probably be when you are in the heat of solving a final exam. The second part of both questions is simulating the denormalization and the operation. So here there are both adding up, but sometimes we subtract. Notice as well saying that these are practice exams for a final and there's only a plus there, but hey, on the final you ask the minus. How is that tricky? Well, it is. These questions are not exclusive. So one has to do the denormalization in both cases. Now our basis is decimal. And if you are unsecure what is 7 plus 3, you can use any technology to help you with this. But be careful, the basis is decimal. So doing everything with the floating point arithmetic will not give you the correct answer for this question. So these two questions, if you like, are very much trivial. And but you have to simulate the floating point arithmetic number system. So in this course, it's what is the answer is important, but also how do you justify a calculation? So why is the calculation the way it is? So this is not the purpose. There is no explaining to do, but in showing your work, you will actually show why the sums are the way what they are. So again, if you are pressed in time, then this is almost the most important slide of this lecture, and one can look now back to the lecture solving these exercises. So the lecture can be viewed from in the opposite order. So the lecture at some point got extremely technical. The purpose of these two exercises is that you go back to the concepts and the definitions. All right, so I started with the definition for numerical analysis that I copied from Siam News. So there is the least. So what is numerical analysis? So you can also say, where are these numerical analyses and where to find them? Well, you can find them in the Society of Industrial and Applied Mathematicians, and you can also find them in the IEEE Society. So these three references are for more overview. So the second reference is definitely recommended for reading. It has some nice pictures in there, what can go wrong if people do not understand floating point arithmetic. The first reference is the handbook, which is a quite good reference, and you can see the number of people, number of authors here, that this is a very strong topic. Many people are involved in this. So the third reference doesn't have even authors in this. It's the product of an entire society. So with this, I conclude this second lecture, and in some sense, the first introductory lecture on numerical analysis.